Hello everyone, welcome back to the course on architectural design of ICs. So, in the last class we have seen that means how efficiently we can implement the algorithm into the architecture. So, as an example of that we have seen the design technique for one that means n-bit generic incremental design. Okay. So, initially we have started with what? Initially we have started with 4-bit incremental design. Okay. So, whenever we have initially we have followed the general method for designing any circuit, that means we have drawn the operation table, then from the operation table using this Carnot map we have tried to find out each of the expression for the output bits. Okay. And then we have realized that for 4-bit it is still manageable. Okay. So, beyond 4-bit, that means if I consider 6-bit or 8-bit or more than that incremental design. So, at that time by following that method, that becomes too much of complex. Okay. So, for that reason what we did is that we have tried to find out different method. Okay. So, as we know that this is nothing but, that means one incremental means that is the addition of two numbers where one number is fixed to 0 0 1. So, from that we have seen that means that is for added with 1. So, again we can do, that means if I want to add it by 2, if I want to add it by 4, or if I want to increment that means circuit by 8 also. So, at that time what will happen? So, if I just take the example, then so at that time what will happen? So, in the incremental design, so for n bit incremental design, what was the expression? The expression was something like this, is n minus 1, if I just, that was a n minus 1 XOR with a n minus 2 a n minus 3 up to a 0. Okay. So, this was the, that means expression for n-bit incremental design. Okay. So, now this is only for if I want to add it by 1. So, we have seen that for 4-bit the S0 bit was nothing but A0 bar and S1 was A1 XOR with A0 and S2 was A2 XOR with A1 and A0. Okay. And S3 was something like A3 XOR with A2, A1 and A0. So, this is for if I want to add it by 1. So, if I just want to add it by 2, that means 0 0 1 0, at that time what will happen? That means at that time only this particular for 0 0 0 1, whenever this position is basically 1. So, that means that is affecting the bits which are on the left hand side, that means from towards the MSB side. Okay. So, as I am adding at the LSB position, I am adding 0 here, that means that bit will be remain unchanged, and from where we are adding 1, from there it will try to follow this particular equation. Same things will happen for if I want to add it by 4. So, at that time that means these two bit position is 0 0. So, this will remain unchanged, and that means this corresponding this particular equation will start from this particular bit position. Okay. The same thing will happen for 8 2. That means, at that time these 3 bit positions will be remain unchanged, and the changes will be occurred from this particular bit position. So, that means now I can develop or I can design any n-bit incremental design which can increment by 1, by 2, by 4 or by 8. Okay. So, next we will see Next we will see another example. Okay. So, that is this. Next we will see another example, that is 4-bit that means decrementer design. Okay. 4-bit incrementer, what we are doing in incrementer, we are just adding it by 1. In decrementer, what we will do, we will just decrement it by 1. Okay. So, here we will again we will follow the same procedure, like here we will try to find out the expression for 4-bit first, then we will try to find out can I apply those expression in terms of that means n-bit representation. Okay. So, that we will try to follow. So, in decrementer design, okay, if I just draw the corresponding so, if I just want to draw it, so in according to the 4-bit decrementer design, what will happen? So, here at this particular side, this will be the input variables, sorry, this is S3, S2, S1 and S0. So, for 0 0 0 0 all will be 1. Okay. For 0 0 0 1 all will be 0, then 0 0 1 0 it will be 0 0 0 1. So, in this fashion this will be continued. Okay. So, this will be continued. So, up to 1 1 1 1. So, whenever I will find out 1 1 1 at that time I will get it like 1 1 1 0. Okay. So, then again using the same procedure, using this drawing the Carnot map, and then I will try to find out the corresponding expression for that. So, instead of doing that, as I said, that is where the problem lies with this technique. So, what we can do, okay, what from this, whenever we are doing decrementer design, that means whenever we are designing it or calling it as a decrementer, at that time what we can write, if you just see, that means from the previous things, if you see, that is 0 0 0, then at that time it is 15, 0 0 0 1 at that time it is 0, for 2 this is 1. So, how we can just do it, if I just in incrementer design, what we have done, 1 bit I fixed to 0 0 0 1. So, in decrementer the same thing, if I just add it by 15, as I am considering 4-bit here. So, if I just add it by, instead of 1, if I just add it by 15, at that time it will work same as the corresponding decrementer design. How? So, initially if you consider 0 plus 15, that means it will give you 15. So, then 1 plus 15, it will give you 16. So, 16 means if I am considering the output of 4, 16 means what? In binary representation it is 1 0 0 0 0. So, if I consider only this particular 4 bit, I discard this particular MSB. So, at that time this will become 0. So, then 2 plus 15 means equals to 17. So, that means this is 1 0 0 0 1. So, this will be, this is discarded. So, this will be 1. Then in this fashion, for 3 plus 15, 18, 18 means 1 0 0 1 0. So, here this is, so this will be 2. So, that means if I just with this is my input A, okay, and this is fixed, this is my input B. If B is fixed to that means 15, then the corresponding addition that means the full adder circuit, if I just put it like this, this is my A and this is B. If I B, instead of in incrementer design, what we have done, I have set these B values to 1 and we have got the corresponding expression for incrementer. But here what we have to do, we have to add it by 15. So, then this circuit, the same circuit will be that means act as a decrementer design. So, whenever we are putting this 15, so at that time will there be the change in the logical expression, that we will see now. Okay. So, how we will see? So, for that what we have done in the incrementer design, so the same thing we have to do in this case also. So, that means here if I consider that means each of these as, that means 4 bit means 4 full adder cell I require. Okay. So, this is A3, this is A2, this is A1, this is A0, and this is the carry which has been forwarded to the MSB side, and this carry is basically cancelled, that means I am discarded this carry out. So, this is the carry in. So, C in equals to 0. So, and all these B bits they are set to 1. Okay. So, now for S0 what will be the expression? That is what we know, that is for any sum the expression for that is A XOR B XOR C, and for carry that is AB plus BC plus CA. Okay. So, here for S0 what will be the value? A0 XOR with 1 XOR with 0. So, this means whenever in XOR gate if any of the input is 1, so at that time if I consider 2 input XOR gate, if one of the input is 1, so at that time it will produce you the inverted of that. Why is so? Because if you just see the XOR, that means the expression, that is what? A B bar plus A bar B, correct? So, if I fixed this B as 1, okay, so at that time what will happen? This is 0 and here B is 1, so it will be A bar. So, that means if I fixed any values, any of the input to 1, so at that time you will get the inverted of that in the XOR gate output. Okay. So, that means now it will be what? A0 bar, and we have to find out the C0, and C0 is what? C0 is C1 and this is C2. Why I need to calculate this C0, C1 and C2? Because this carry, if this bit is 1, okay, so at that time the carry which is being generated in this particular full adder, this particular full adder, that will affect the corresponding next of it, the adjacent full adder cell, it will, the carry will affect. So, that we are just basically traversing to the, that carry is propagated towards the MSB side. Okay. So, now for carry we have also calculate for this particular full adder cell. So, carry will be what? A0, that means A plus B means AB means here B is 1. So, A0 plus for B and C this is 0. So, for C and A that is 0. Okay. So, carry is A0 in this particular case. So, then next for this particular full adder cell what will be the expression? So, S1 is here A1 XOR with 1, then here carry is what? Carry is not 0 here, carry is basically A0. So, this is A0. So, I can write S0 S1 as XOR with A0 bar. Okay. So, then again what will be the carry 1? Carry 1 will be A1, AB means A1 plus BC, BC means what? A0 plus CA, CA means what? Here A1 and A0. Okay. So, A1 and A0, if I just take it common something like this, A0 into 1 plus A1, what I can write this expression as A1 plus A0. Why I can write this A1 plus A0? Because 1 plus A1, if we follow this De Morgan's theorem, 1 plus A1 means that is nothing but 1. Okay. So, that means A0 into 1 means that is A0, that means that is A0. So, this expression I have simplified, or I have, if I minimize this particular expression, I will get that is as a A1 plus A0. Okay. So, that means carry 1 is now A1 plus A0. So, what will be the expression for S2 now? The S2 expression is here A2 XOR with 1, then XOR with A1 plus A0. So, this S2 expression what I can write? A2 XOR with A1 plus A0 whole bar. Okay. So, then again if I try to find out the corresponding carry out expression. So, carry out expression now what will be? That means for AB that is A2 plus for BC that is A1 plus A0 plus what? That is for AC that is A2 into A1 plus A0. Okay. So, then the same thing using this, that means if I just consider a new page, if I just take this C2 as what? A2 plus A1 plus A0 plus A2 into A1 plus A0. So, if I just want to simplify this particular expression, then what will happen? A2 plus A1 plus A0 plus A2 into A1 plus A2 into A0. So, then again if I take it common as A2 common, that means within this and this, if I take common, so A2 plus A into A1 plus if I take common of this A0 and this. So, then at that time what will happen? Here A1 is remain same. So, A0 is common 1 plus A2. So, 1 plus A1 is nothing but 1 and 1 plus A2 is nothing but 1. So, that means now what I can write this expression as? So, that means now C2 becomes A2 plus A1 plus A0. Okay. So, now next again then for S3 what will happen then? For S3 what will happen? The bit is A3 then with 1 and then the C2 value is this is A2 plus A1 plus A0. So, this means this is A3 plus A2 plus A1 plus A0 whole bar because of this one. Then that means now we have find out the expression for what? That 4S value, the 4 output value. How? Here this is the expression for this S3. Okay. If I just go back, this is the expression for S2, this is the expression for S1, this is the expression for S0. So, that means now I have find out S0, S1, S2 and S4 by this particular technique. Now, so from this can I generalize this particular equation? If you follow that, whenever we are just, that means traversing to the MSB side, the corresponding bit is this is XOR, that is XOR with the lower side, that means the next corresponding bit which are OR to each other, and then inversion of that. That means from this particular equation, if I want to make it generalized in generalized form, so at that time what will happen, or what I can write, that is Sn equals to Sn minus 1, that will be An minus 1 XOR with An minus 2 plus a n minus 3 plus up to a 0. This is OR and whole bar of it. So, this is the generic expression for any n bit in decrementer. So, now you can put this n value to any value, that means whether that is 4, 6, 8, 16, whatever value you just put it and get each of the corresponding, that means sum value, that is if I consider 8. So, sum 0 to sum 7 you just find out, and in this using this particular equation you just find out the expression for each of that, and then you just map it to the architecture. Okay. So, now if I just want to, that means this 4 bit this expression we have got. Now, if I just want to map it to the architecture, that means whenever you have got this particular expression, now you can write this expression using any HDL language. So, whenever you do the synthesis, at the time that will be converted into the corresponding gate level netlist. That means that will be implemented using the corresponding gates. So, now if I just that means draw the corresponding architecture for that. So, at that time how it will look like? So, it will look like for S0, what is there? For this is A0 and this is S0, that is the inversion of that. So, in the next that is A1 x nor with A0, that is S1. Okay. So, then what is there? I need OR gate. In incrementer I was needing AND gate, but here I need OR gate. So, that means OR gate that has to be this is A2, which is OR with A1 and A0, and that means x NOR with A1 plus A0. Then again for S3, this is A3, okay, and here also I need one OR gate. So, this is one of the input is this one and another input is this one. So, here what I am doing A2 plus A1 plus A0, which are XNOR with A3, and this will give me S3 value, this will give me S2 value. So, if I just want to make it for n bit, so n bit means here what will happen, there this will be this. So, this will be connected to a n minus 2 and this will come from the previous OR gate output, and then it will be XNOR with the corresponding a n minus 1. So, this will give you S n minus 1 value. Okay. So, this is the, that means architecture for the 4 bit decrementer. Okay. Understood? Then again if I just want to just go back to the slide. So, that means this now in this that means we have learned how to design any that means any n bit decremented design. So, now next what we have to do, we have to see one's complement circuit design. Okay. So, one's complement, in one's complement what we do, in one's complement we do basically, suppose whatever input we give, it will be just inversion of that. That means draw it, that means in one's complement circuit, if I consider 4 bit, so at that time what will happen? So, this is A3, A2, A1, A0, this is S3, S1, S2, S1 and S0. So, this is the nothing but 1's complement circuit, but I need controlled operation of that. That means, if I put enable signal, then only it will give me this 1's complement circuit, otherwise it will remain unchanged. So, for that, what will be the changes in this? What will be the changes in this particular circuit? So, in the just previous case, what we have seen in XOR gate, if one of the input is 1, so at that time the output of that particular XOR gate is the inversion of the other input. So, instead of this inverter over here, if I just put it the XOR gate for each of this particular, instead of this inverters, sorry, I am designing X naught. And here each of this input is like, this is A3, this is A2, this is A1 and this is A0, and this is connected with this is S3, this is S2, this is S1 and this is S0, and this is the enable signal. So, according to the logic, what will happen? If enables equals to 0, if enable equals to 0, at that time it is unchanged, that means this is the functionality, and if whenever it is 1, so at that time it will give me 1's complement. Okay. So, this is the circuit where I can do this controlled 1's complement circuit. So, if I want to make 2's complement, so how we do? In 2's complement, initially how we can do? Initially is that we do 1's complement, then with that 1's complement, if you add 1, then that will become 2's complement. So, that means there is option where or by which I can do in one particular circuit, I can implement both the things, that means in 1's complement as well as 2's complement. So, that we will discuss in the next class. Thank you for today's class.